Hello all of you. So, in the last class I have been discussing the interaction energies or the potentials that we use in a molecular simulation, and before that we have discussed the molecular dynamics simulations. That is one way to sample the phase space. So, today I will introduce the Monte Carlo simulation, that is another way to sample the phase space or another method of molecular simulation. So, I want to go back to the drawing that we had of the phase space, and we have said that I can represent the state of the particle on something known as the phase space, where P essentially is the coordinates of the particles and Q is the P is the momentum of the particles and Q are the generalized coordinates of the particles. So, I can represent any point on the phase space as Q and P, and in molecular dynamics what we do is essentially we look at the trajectory gamma t as a function of time, of course, for a finite time. So, in this kind of a picture, there is something that is defined, there is a theorem that is called the Liouiville's theorem, which essentially says the following. So, what we imagine that the phase space is some kind of a hypothetical fluid. I mean, we are not plotting in like typical coordinate like xy axis. So, we should not think of any kind of a real fluid, but some kind of a hypothetical fluid because it is moving. So, you can move from one point in the phase space to another point. So, that motion we can characterize as some fluid moving within the phase space. It is not really a real space in terms of coordinates. You will not see that happening in this particular way because it is not really a space that we can visualize because it is 6-dimensional space. So, the fluid is somewhat hypothetical, so as to speak, but the definition of that undercoat fluid is useful in defining this particular theorem of it is defined on the phase space. It says that that fluid that we can imagine in the phase space is actually incompressible. So, we make an analogy with incompressible fluids in fluid mechanics and think of the hypothetical fluid, that is the phase space, as an incompressible fluid. So, what this essentially means are two things. First, we are essentially saying that systems are neither created nor destroyed. So, clearly I can be anywhere in the phase space at any given time or any given spatial location, and all these are valid starting point for us to visualize how the system is moving, right. So, in some sense each of these phase points, each of these gamma values are different systems, so as to speak. So, when I am looking at the trajectory in the molecular dynamics, I am looking at a particular system starting from one particular gamma value. Now, that system remains. Of course, the gamma of that system will change, but that system is not being created or destroyed. Similarly, you can have some other system that is here to begin with, and then it is like going in this particular way. So, you can define systems as different individual states, and at any given time I can identify a system that is moving with time. If I look in some other time, I will look in some other system moving with time, but all these systems are essentially always present in the universe of the phase space, because there is no creation or destruction of the system, they evolve over time. And as a result of that, what we can then say is that if I look at any small volume in the phase space, let me define the volume as some d gamma, it is like a small range of possible values of gamma. Now, of course, that d gamma is also going to evolve with time, and in the phase space plot, it is quite difficult to visualize what it will look like, but clearly the shape of that small d gamma may not remain same. But since the systems are neither created nor destroyed, what we can then say as a consequence of incompressibility assumption that I am saying is that the volume of that phase space element is constant. That is similar to like what happens in an incompressible fluid. In an incompressible fluid, what do we say? We say that the density remains constant. So, if I look at any small volume in the fluid, that is the fluid element, that volume remains the same. The fluid of course moves, that the shape of the volume may change, it may distort, it may get shrink, whatever, but the volume of that cannot change, because overall the density of the system is constant. So, if the volume of an element changes, that would necessitate a change in the volume of the entire system, and since that is not happening, the volume of the element is also not happening, and therefore, we say the fluid is incompressible. The same idea also applies here. Since the systems are neither created nor destroyed, we can imagine the phase space as collection of many of these systems, each of which are evolving in their own way, but their volumes remain constant. So, they fill the phase space and there is no way they can expand or shrink in terms of the volume. Their shape may change, but the volume of the element will remain constant. Mathematically speaking, this means the condition that the total derivative of rho is equal to 0, right, and that is true regardless of whether we are at equilibrium or not. It has nothing to do with equilibrium. This is simply coming from a standard principle in classical mechanics. There is no thermodynamics involved in whatever we have discussed in the Liouiville's theorem. Now, this total derivative d by dt is actually defined in kind of a frame that is moving with the fluid element. So, I am looking at a derivative with the rho with respect to time as I am moving with a particular fluid element, right. So, this derivative can then be represented as the partial derivative with respect to time and derivative with respect to the momenta and derivative with respect to the coordinates, right. The other way to think about it is, let us say if I am going from this point to this point in phase space, when I am computing the d by dt, I am moving with the point, right. Let us say if I am going from A to B, I am moving with the point. So, my frame is also moving from A to B and derivative is defined in that particular frame. On the other hand, if I compute the partial derivative, that will be fixated to the point A. So, even though that particular system at A has moved to B, it has evolved to B, our reference frame for the computation of the time derivative dou by dou t will remain fixed at A, right. So, this is keeping the P and Q constant, right. So, if I do the math, it turns out that I can represent the total derivative as the partial derivative plus p dot dotted with del of p, so gradient with respect to the momentum, plus q dot dotted with the gradient with respect to q, right. So, the gradient operator is defined as it is. So, in the first case we are defining the gradient with respect to the momentum, and again these are with respect to the 3n momentum variables that we have. So, you will have 3n components in the del of p, right. It look like something like a unit vector in each of the momentum directions, dou by dou pi, where I is going from 1 to 3n for all the momentum variables, and similarly we can do the same for the coordinate variables. So, then this quantity is defined as the Liouiville operator and it tells me that my d by dt can now be represented as something like dou by dou t plus I L. By the way, this is the complex I, and this I is not same as that I. This I was an index ranging from 1 to 3n, and this I right here is the complex I. So, I square is equal to -1. So, that means since the Liouiville theorem says that d rho by dt is equal to 0, what we have is dou rho by dou t is equal to minus I L rho, right. So, this I can then integrate as something like 1 by rho dou rho is minus I L dou t, which using the initial condition that rho, so rho is clearly a function of the phase space at t equal to 0 is equal to something like rho gamma 0, right. So, therefore, what we have is rho gamma t is equal to rho gamma 0 exponential of minus I L t. Keep in mind that in the exponential the L is the operator, L is not really a number. So, therefore, we can expand it, but it still remains kind of an operator, just like dou by dou t is an operator. So, only when it is applied to something it has some meaning. But nonetheless, what this gives rise to, and I will not really go over the math, is that this gives us the fact that if I go to a large value of time, that is if I go in the limit of t going to infinity, this will tend to some stationary solution. Let me call it something like rho bar, that is the stationary solution. Let me call it rho bar as a function of gamma, right. So, over time, since you are multiplying with an exponential function and it is a decaying function kind of, although keep in mind that L is an operator, but nonetheless it tends towards some kind of a stationary solution, right. So, this has certain consequences, right. So, one of the consequences of this result is that I will of course start with some distribution of the probability density in the space, and this is going to evolve with time, but provided I wait long enough, I will reach an stationary distribution of probability density in the phase space, and this is what we refer as the equilibrium state of the system, right. So, I will repeat this point here. So, when we begin or when we start looking at any particular system, or when the system is not in a condition of equilibrium, the system has some probability density. That probability density as a function of the phase space point gamma is changing as a function of time until we reach the equilibrium state, and at equilibrium state it becomes a constant value. Of course, it remains a function of the phase space point, the phase space variable, but it is no longer a function of time, and that is what we refer as the equilibrium state of the system. After equilibrium, that probability density no longer changes, so as to speak. So, this is very much in line is our idea of the ensembles, right. So, when we said that I will look at my ensemble as a collection of states, it clearly corresponds to different points in the phase space, and clearly at all of these points, if I start looking at the rho gamma of t, that probability density will keep on changing with time, and only at the equilibrium state this goes to something that is independent of time. But in ensemble, we always define the probability density of a given state. So, we implicitly assumed that the probability density is kind of independent of time, and that is the equilibrium state that we are referring to, right. So, that is one of the consequences. The second consequence is, if for example, let us say if I am at A, that is some particular phase space point gamma. If for example, from here I go to a new state, that is, let me call this something like gamma plus 1, just for the sake of convenience. Let us say in any given time I go from gamma to some gamma plus 1. Now, this particular phase space point A will therefore in some sense get empty, because we have moved from gamma to gamma plus 1. But since the fluid is incompressible and since the probability density is stationary, what this means is something else needs to come at this particular point from gamma minus 1, that is a past state, right. So, as soon as a system leaves a phase space point, some other system occupies that phase space point, because if that does not happen, then the probability density will not remain constant, because at any given point you should have an stationary value of the probability density. As soon as the system has moved from there, clearly the number of systems or number of states at that particular point has decreased. So, that means that unless something else comes there to fill in the void, the probability density cannot be constant, right. So, this means that something else must come to that particular point if the system is at the equilibrium state. And this has a very deep consequence, not only for the Monte Carlo simulation we will discuss, but also for the molecular dynamics simulation. Why is that? Because I have said that although the system in principle can be just anywhere in the phase space to begin with, I am starting from a particular phase point and I look at the trajectory over a finite time. So, clearly if I started from somewhere else, you may have some other trajectory, right. What it tells me is that as soon as this previous state, as soon as, let us say if I am following this particular trajectory, as soon as I leave from here to there, let us say from point P to point Q, something else must come at P. So, that means some other trajectory must be coming at P as soon as the trajectory of the system that I am looking at has moved from P to Q. So, as soon as system moves from P to Q, some other system occupies P. So, the other trajectory should pass through or cross the trajectory that we are considering. We are not actually doing those trajectory, we are looking at only one point system, but we know that some other trajectory is also crossing this trajectory at every point, because as soon as I leave every point on the trajectory, something else must come there if the system is at equilibrium. So, this means that since the trajectories cross each other, we can therefore say that I need not look at all the possible trajectory, because ultimately if I keep following the same trajectory over time, that is in some sense a representation of all the trajectories, because that trajectory that I am following for one given system is being shared point by point by every other trajectory. Every other trajectory is crossing each of the points of this particular trajectory, provided if I look at it long enough. So, there is no unique point on the trajectory that I am considering that is not being revisited by any other trajectory in the system. In fact, every point that I am passing through will be visited by some other trajectory at that particular time when I have moved past it, right. So, therefore, if I look at any given trajectory for very long time, that is in some sense equivalent to looking at multiple trajectories, because ultimately every trajectory is a collection of points and every point is being visited by one trajectory or the other as the time passes, right. So, when I have traced a trajectory for one particular system, I have been basically able to look at the trajectory of all possible system, provided that I have evolved long enough, right. And this is the idea of ergodicity, right. So, an easier way to think about it is, let us say for example, if I look in air in this particular room, that is a much easier example. What I am saying is kind of saying that every molecule in this particular air will eventually pass through every other point in the room, provided I wait long enough, right. So, in this case I am only looking at the coordinates. So, every molecule is having some trajectory now in the real space over time, but every time I am passing through any particular point in the air, some other molecule will occupy that point, right. So, therefore, if I just keep following one particular molecule over time, it is essentially capturing the entire room, because any place in the room can be occupied by the molecule, but we do not know how long it takes. But if I just keep waiting for very long time, this trajectory of a single molecule will pass through every point in the particular room. So, in a similar manner, now in the phase space compared to the air was a real space, now it is the phase space. Now, in the phase space, since trajectories cross each other, if I just wait long enough, I will be able to basically sample the entire phase space. That is a very deep consequence of the Liouiville's theorem, and this essentially gives rise to the idea of the ergodicity in the system, right. It is not always true. There can be systems which can be non-ergodic. So, for those systems, what will happen is that there will be regions in the phase space that will not be visited starting from any given state. So, let us say for example, if I start from a given point, I only visit part of the phase space and some part is never visited. If that is happening, then we can say that the system is non-ergodic. But when it is ergodic, and that is the assumption that we typically make, then we can say that no point in the phase space will remain untouched by the system, no matter where I start from, provided I evolve the system for a very long time. So, that is one important consequence that goes into the idea of molecular dynamics. Then there is another consequence that is important for the Monte Carlo simulation, and that is, what this means is, since my rho gamma is independent of time, why does it matter that I look at trajectories starting from any given point? Because in the end I am interested in the stationary solution. In the stationary limit, rho gamma is independent of time, right. So, instead of looking at dynamics of any given system, what I can instead do is I can sample points in the phase space in some other way, and precisely this is what we are doing when we are defining the ensemble. So, an ensemble is a collection of states where we are not interested in how will I get from one state to the other. I simply list out all the possible state, and once I average over the properties in all those states, I get the average behavior. So, I am not really concerned how the states are connected, or I am not concerned about the dynamics of one state going to the other, right. When we are concerned about it, we can do a molecular dynamics that is actually a fair representation of that, provided I wait long enough. So, if I just pick two states from ensemble, yes, it is true that they will be connected by some sort of a trajectory, but how long that is going to be, that we do not know. It may take a very small number of steps, it may take a very large number of steps, right. So, instead of trying to connect the states, instead of looking at dynamics from a given state and all that, what we can instead do, as done in the thermodynamic ensemble approach, is we simply sample the phase space without worrying about the dynamics of those points, and that is only valid when we are at the equilibrium condition, right. So, in Monte Carlo simulation, this exactly is what we are doing. We are simply sampling phase space by looking at a large collection of points in phase space. Okay. And then we can sample in a variety of ways, and we will discuss how can we sample that, but you can already see the beauty of this. Let us say, for example, I am looking at two particular phase space points A and D. So, in a Monte Carlo simulation, I can clearly sample A and D very easily, and these are arbitrarily located at different places in the phase space. On the other hand, if I am following the molecular dynamics approach, then I will start a trajectory from A or from D, and I have to wait long enough until they meet each other, right. So, starting from A, we can never be sure that I will get to D if I am following the molecular dynamics. But in Monte Carlo, it is trivial to do, because I can always sample A and D, because I am not worried about how A is evolving, how D is evolving. I am only interested about stationary states A and states D, right. I will have some mechanism to choose how will I generate the states, that is a secondary point. But let us say if I am interested in a particular state, I can always pick that, and I can pick a collection of states that I am interested in. So, what this means, it is Monte Carlo, provided that the scheme has been designed appropriately, it is easier to explore the phase space. I can pretty much pick points the way I like. On the other hand, in molecular dynamics, it is much more difficult to explore the phase space. The demerit, however, is there is no dynamics, or we can say there is no true dynamics, because we are not following Newton's laws of motion. There, of course, when we are doing simulation, we have some mechanism to generate the points, and that may appear like some kind of a dynamics, but it is not following the Hamilton's equation of motion. It is not starting from Hamiltonian, and therefore the dynamics is not really a true dynamics. On the other hand, in molecular dynamics, as opposed to the Monte Carlo, in molecular dynamics, it is having the true dynamics. I can really capture how any state would evolve, particularly when we are looking at the behavior in the non-equilibrium regime, when we have not reached the stationary solution. In that case, molecular dynamics will kind of guide the study of how the system will evolve to the equilibrium state, and that will be a true dynamics because we are solving the Newton's laws of motion or Hamilton's equation of motion. On the other hand, it will be difficult to explore the phase space. We are limited by the natural trajectory of individual states, and the natural trajectory may take very long time to explore the entire phase space. It may not be efficient in many of the situations, right? Nonetheless, as long as we are interested in the equilibrium state, both should give you the same answer, right? Because ultimately, in both the approaches, we are trying to sample the entire phase space, we are trying to get the probability densities, and on basis of those densities, we want to evaluate the average properties. So, whatever rho gamma we will have here, the same rho gamma we will have here in the equilibrium state. So, therefore, the equilibrium behavior must be the same between the molecular dynamics and Monte Carlo simulation, provided we can get to the equilibrium state. That is naturally true, right? So, when I start a simulation, I am not certain, and that is true also for Monte Carlo simulation, we will discuss that point later, that I am actually simulating a thermodynamic equilibrium. Am I correctly representing the density of states as what should be in the equilibrium condition? If I am able to do that, then in that case, we will have the same equilibrium behavior, because then we are studying the equilibrium. If we are not able to do that, then in molecular dynamics still it is fortunate, because we are still capturing the non-equilibrium behavior. The dynamics whatever we are following is still valid, but in Monte Carlo it is kind of meaningless, because dynamics is not the true dynamics, and as long as we are not in the equilibrium regime, that simulation is pretty much meaningless, because Monte Carlo hinges on the idea of the stationary solution of the probability density. That is when the probability density becomes independent of time. As long as that condition is not met, the Monte Carlo does not have any meaning, right? Having said that, you will read some approaches, and I will also discuss this towards the end of this course, where Monte Carlo is applied in non-equilibrium settings. But in what we will discuss in this week and the following week, we will be confined to equilibrium simulations. Whenever we apply Monte Carlo in the non-equilibrium setting, it is not still the true dynamics as molecular dynamics, but there are some ways it still captures some sort of physics, right? So, it is not really a very correct way to simulate non-equilibrium behavior, but nonetheless there are methods called kinetic Monte Carlo scheme that can do that, and we will discuss it towards the end of the course. But for most applications, Monte Carlo is applied in the equilibrium setting. Molecular dynamics also in most application tries to simulate equilibrium behavior, because that is what is of practical interest. But there are cases when molecular dynamics is also used to look at the non-equilibrium behavior of a system. So, with that I want to conclude here. Thank you.